but with an undergraduate background in physics. And then I veered off into structural engineering, and I come to it from a building envelope rehabilitation perspective. So put physics and structural engineering together, I know sort of the deepest and darkest theory and the muddiest practical application of building envelope technology. But I made a pact with John and with Eric. If you guys start asking me about mechanical engineering subject matter, they will jump up and help me out here. So what I would like you to walk away from this talk with are some learning goals. Essentially, what makes a building envelope, the barriers that we put into the building envelope that take care of certain functions to keep out water, air, vapor, and keep energy in. I'm going to cover briefly traditional masonry building envelope construction and common building envelope rehabilitation needs and problems. Then I'll get into technical consideration for exterior wall upgrades, as you might encounter when you want to rehabilitate historic buildings, and I'm going to talk about opportunities and technical risks of those upgrades. And I'll spend quite a bit of time on an analytical and investigative approaches to envelope performance and computer modeling tools for thermal and hygrothermal performance evaluation. And then I will tie it all together with a case study of a project that I worked on years ago. As the first part, I'll just cover some building envelope basics. When we design a brand new building today, we expect it to have at least 3 functional components, 3 barriers: a water barrier, an air barrier, which is required for energy efficiency and to limit moisture accumulation, and a thermal barrier, insulation. Some walls also require a 4th barrier. Sometimes it's required by code, a vapor barrier, which is also required to limit moisture accumulation, and you need that if you have, say, a high-performance building where you're trying to contain a high humidity building interior. It's a very important part to remember in the context of my talk is that these components are interrelated systems. Their configuration and relative placement is very critical. One affects the other. Frequently, the materials that we use combine the functions of 1, 2, or even 3 of these in one material. So the interplay is very important, and it requires some technical analysis to review, particularly when we start retrofitting any of these into historic buildings to bring us improved performance. Carl already had his hand up. Go ahead.
And if I ever pretend to know anything about building envelope design, well, I'll pick up the phone. I'll call you. But so, can you just spend a minute because no matter how many times I've read this, whatever, it's still total confusion in my mind. The difference between a vapor barrier and an air barrier.
Well, I'd be happy to entertain that and talk about that. There is a danger that we might not get through the rest of my talk. All right. Start with the beginning, Carl, right? Medial envelope 101. Water barrier keeps bulk water, liquid water out, right? Things that do a good job of being a water barrier are, for example, asphalt saturated felt, right? Put that behind the cladding, it does a good job of collecting the water, conducting it to the outside. Right? Asphalt saturated felt, though, because it has laps, is not a good air barrier because the air can sneak in between those laps, and it's also not a good vapor barrier because the matrix of the asphalt is not really sufficient to retain the vapor. An air barrier resists airflow across a building envelope, right? So a good example of something that is primarily an air barrier is, say, your Tyvek, right? It's a material, it also has some water barrier properties, but we'll forget about those for a minute, right? What it does is it resists airflow across the envelope, right? So say if you have differential pressure across the envelope, you have, for example, for a museum, you'd like to have higher interior building pressure so you're not dragging in nasty air from the outside. That Tyvek air barrier is important to keep that contained and keep it from traveling across the building envelope, right? The important thing about an air barrier, and I'll get to that later, is that it is continuous. Right? If you have an air barrier, if you might have just a little wee hole somewhere, because air can carry a tremendous amount of moisture, right, that can cross the building envelope through that little opening, your air barrier is substantially compromised. Okay, that's the air barrier. You with me? Okay. Thermal barrier, that's the easy part, right? We've had a lot of mechanical engineering talk. That's your insulation. Now, your vapor barrier, that is there to resist the movement of moisture vapor, right, on a molecular level. So it has to be very dense so that the water molecules can creep through there. So it has to have a very dense matrix, something like polyethylene, right? Poly sheeting is a good vapor barrier. Self-adhered waterproofing membranes, great vapor barrier. Right? Your under slab, thick poly that you put under there, TPO, great vapor barrier. Right? This most typically gets combined with, as an air barrier and a water barrier. And a typical example of that is your self-adhered wall membrane that keeps water out, air out, and also resists vapor. Good enough? Okay. Let's talk about historic mass masonry walls, right? This is what we're all here to see. We went to the church yesterday. These walls really resist water penetration fundamentally differently than a modern cavity wall, right? They don't have a dedicated water barrier. There's no Tyvek in there. The way those walls function is that they essentially function as a reservoir. They soak up water, and they're predicated on the notion that the water soaks in there when it's rainy, it dries out when it's sunny out, and it just never rains long enough and hard enough for it to soak to the inside. Right? So we provide mass to absorb and evaporate that moisture. Another thing architects did who designed these buildings is they incorporated articulation of the facade, physical shielding, belt courses, recessed windows, to make sure that the water had a difficult time hitting these vulnerable facade elements. Sometimes, if they were progressive, they had some integral metal flashing that they used to protect those walls, but no water, air, or vapor barriers. And typically on buildings of this vintage, say anything built before 1940, you don't see air or vapor barriers or insulation. So really a traditional building method with solid walls, typically a brick backup with a natural stone facing or just brick masonry. And the important thing to keep in mind with these types of walls is that water absorption and drying cycles must be allowed to occur. The walls absorb moisture and they have to be able to let it go again, otherwise the moisture will accumulate and deteriorate the wall system.